Bismillahirrahmanirrahim. Hello everybody. Two exercises on sequences. The first one on Cauchy types of sequences. So this is the first one. And the second one. We will start by the first one. So let Q be a real number between 0 and 1, and let us take UN, sequence, real number sequence, which verifies this inequality, the absolute value of U index n plus 1 minus U index n is less than or equal to Q, the absolute value of UN minus UN minus 1 for n in natural number. The first question, show that UN plus 1 minus UN is less than or equal to Q power n, the absolute value of U1 minus U0. Second question, deduce that UN is Cauchy sequence type. The third question, as an application, show that this sequence is convergent 1. The second exercise, show using Cauchy criterion that we have two convergent sequences and one divergent sequence using Cauchy criterion. Let us start by the first exercise. Show that UN plus 1 minus UN is less than or equal to Q power n, absolute value of U1 minus U0. Actually, we have many methods. I will choose just one, the simple one. For the first question, show that we have this by induction. We will prove that this formula is true. Let us suppose or denoted, let us denote the proposition dependent on n. This proposition UN plus 1 minus UN less than or equal Q power n U1 minus U0. By induction, for n equal 1, we have from this formula, we will apply this formula. We have U index 2 minus U index 1. This is less than or equal to Q U index 1 minus U index 0, which is true. So this one is true for n equal to 1. The truthness comes from this given property. For n equal to, we have U3 minus U2. This is less than or equal to, using the first one, using this one, this is less or equal to Q U2 minus U1. Once again, this is less than or Q power 2 U1 minus U0. So here we use this twice. which is also true. Let us suppose that Pn is true and prove that Pn plus 1 is true too. Pn plus 1 can be true if we can verify that un plus 2 minus un plus 1, this is less than, using the first one, this is less than q, absolute value of un plus 1 minus un, and this one verifies q power n u1 minus u0. This inequality is true because we suppose that P of n is true, the induction hypothesis, but actually here we can write that q n plus 1, the absolute value of un minus u0, and this inequality actually is here, which means that un plus 2 minus un plus 1 is less than or equal to q power n plus 1 absolute value of un minus u0. This means that the first question is okay. We finish about the first question. How about the second question? Deduce that un is Cauchy. We say that the sequence un is Cauchy, or Cauchy's sequence. This is equivalent with, for all epsilon greater than 0, we can find, if we can find the rank n of epsilon from n, such that for all n and m greater than or equal n of epsilon, we have un minus um less than epsilon. Without loss of generality, we can suppose that m is greater than m. Since n is totally ordered as a part of R. We might start by un minus um. We can write it as un minus 1 plus un minus 1 minus un minus 2 plus un minus 2 minus un minus 3 and so on. Um plus 1 minus un. Using triangle inequality, this is less than or equal to un minus 1 plus un minus 1 minus un minus 2 plus un minus 2 minus un minus 3 plus un plus 1 minus un. But every single term of this sum verify this beautiful inequality, which allows us to write here q power n minus 1 u1 minus u0 plus q n minus 2 u1 minus u0 plus q power m u1 minus u0, which is less than or equal to q power m, the least one, u1 minus u0, common factor 1 plus q power 1 plus q power 2 plus the last one q power n minus 1 minus n. And here we recognize the sum of geometric sequence the sum takes this form: 1 minus q n minus m divided by 1 minus q. And since q power q is between 0 and 1, so this is less than or equal to q power m times q power m u1 minus u0 times 1 divided by 1 minus q. Since we are just searching a rank, so it doesn't matter from what rank we can start, but we have just to find a rank. We have just to find a rank, and we can, for example, taking just the last one, un minus um is less than or equal to this, so we call epsilon, common epsilon came here, less than epsilon. The last inequality, this one, gives us the right to write q power m less than epsilon times 1 minus q divided by u1 minus u0. The logarithm is an increasing function, so logarithm, natural logarithm, criterion logarithm q less than the logarithm. Let us call this value, let us call it alpha, ln alpha, then m is greater than ln alpha divided by ln q, since ln q is negative. And here we have two cases. If ln alpha is positive, so m is naturally greater than all negative number, real negative number. If alpha is negative, so we have ln alpha, which is negative, divided by ln q, which is negative, so this is positive. It is sufficient. It is sufficient to consider an epsilon equal to the maximum between 0 if the quotient is negative, or the integer part of ln alpha divided by ln p plus ln q, sorry, ln q plus 1. This finished the second question. As an application, let us decide of the nature of the sequence un plus 1 equal to 1/2 sine un. The third question and the last for the first exercise. Let be un plus 1 equal to 1/2 sine un for n in natural number n. If this sequence verifies this property, then with q between 0 and 1, then our sequence will be convergent. Why? Because it is Cauchy, and in R, all Cauchy sequences are convergent, and all convergent sequences are Cauchy sequences in all spaces, not just the real space, real number space. What do we have here? Here we have un plus 1 minus un. This is equal to 1/2 sine un minus 1/2 sine un minus 1, which is equal to 1/2 sine un minus sine un minus 1. But we need un and un minus 1. What we can do here? Yeah, it can work. Yeah. If we consider function f of x, which is equal to sine x, we have sine x minus sine y. This is equal to cosine cxy x minus y using a theorem mean theorem value, mean MTV, mean theorem value, le théorème des valeurs intermédiaires. Then this will be equal to 1/2 cosine c un and un minus 1 times un minus un minus 1 but cosine is bounded by 1, which is less than or equal to 1/2 un minus 1 for all n in n, which means that this sequence is Cauchy type with q equal to 1/2 this means that it is convergent. This means that it is convergent. And this ends the first exercise. Let us move to the second one. Let us move to the second one. We have here un equal to sine k over k square. This is convergent. Why this is convergent? The second exercise. Why this is convergent? Because if we take the difference, so we have to verify the definition. If we take n and m, such that n greater than m, and let us consider the difference un minus un. This is equal to the sum from k equal 1 until n sine k divided by k square minus the sum from k equal 1 to m sine k divided by k square, which is equal to the sum from k equal m plus 1 until n of sine k divided by k square, which is less than or equal to the sum from k equal m plus 1 until a k square. Which is once again less than or equal to the k equal to 1 m plus 1 until a 1 divided by k times k minus 1. We have k square, and here we will take k and k minus 1. This is greater than this one. For the last sum, we will use well-known decomposition. One has 1 divided by k minus 1. This is equal to 1 divided by k minus 1 minus 1 divided by k. We have k minus k plus 1, it's okay. This one, the last one, we will just keep the first and the last one. M plus 1 until n of 1 k minus 1 divided by k. Here we have a telescopic effect from k plus 1, m plus 1, so 1 divided by m, 1 divided by m, minus 1 divided by m plus 1, plus for m plus 2, so 1 divided by m plus 1, minus 1 divided by m plus 2, and so on, until the last one, minus 1 divided by n. They will be constant. We just keep 1 m minus 1 n, which is less than or equal to 1 divided by n. Here we call the epsilon, the famous epsilon, we call it, to put it as a sufficient condition. We put it here, greater than, less than epsilon. So we can take n as integer part. We can take n of epsilon as integer part of 1 over epsilon plus 1, and it will be a Cauchy sequence. For the n, it is so easy. Why? Because it is a kind of geometric sequence with q equal to 1 divided over 3. Vn minus Vn. This is this is less than or equal, so I will be a little bit fast. Less than or equal to k equal m plus 1 to n, 1 divided by 3 power k. So we start from m plus 1 here. Less than 1 divided by 3 power m plus 1 times, we have 1 plus plus until n, which is equal to 1 minus 1 divided by 3 power m power n minus m divided by 1, which is less than or equal if we take off this, so it will be less than. We have 3, which means 2, so 3 here. We have 1 divided by 2, 3 power n. We call epsilon here to put it here, less than epsilon, and from this we can easily get m. So we have m, epsilon, we have m greater than m, so we have ln 3m epsilon 1 divided by 2 epsilon, so ln 1 divided by 2 epsilon divided by ln 3. If this value is negative, it's okay, all m verify. If this is positive, so we can take n of epsilon, it's equal to the maximum between 0 and the integer part plus 1, the integer part of a, let us call this a. This answers this question. So it is convergent. The last one, Wn for this exercise, the last one, it is an harmonic sum which is divergent, and let us prove it by showing that it is not Cauchy. Wn is equal to the sum from k equal 1 to n, 1 over k. This is divergent. Why? Because if we take the negation of Cauchy sequence, there exists epsilon greater than 0, such that for all n in n, we can find n and m greater than n, and the difference is greater than epsilon. For example, if we take n greater than m, without loss of generality, we can consider this. If we take n equal to m, or n equal to 3m, or n equal to 4m, or n equal to 5m, and so on, it can make sense. It gives us a counter example. It gives us the confirmation of this negation of the proposition. The proposition such that un is Cauchy, so it is Wn isn't Cauchy. We just try this one. Oh, no, we will try this one. Actually, if we consider u3m minus um, this will be from the sum from k equal to m plus 1 until 3m of 1 over k. The least one, the smallest one, is for 3m. So this is greater than 3m minus m minus 1 plus m means 2m. This is greater than or equal to 2m, strictly greater than 2m. 2m means 3m minus m minus 1 plus 1, the number of terms. And we will take the smallest one. The smallest one is for 3m times 1 divided by 3m, which is equal here to 2 divided by 3. So for epsilon less than, greater than, for epsilon equal, for example, to for epsilon equal to 2 divided by 3, or strictly less than 2 divided by 3 and greater than 0, for all epsilon, we find for all epsilon. So this is just if we find one, but we find an infinity cases. All epsilon, such that epsilon is between 2 divided by 3, 2 over 3 and 0. We find n and m in this form, such that the difference is greater than 2 divided by 3, which means that this sequence is not a Cauchy one. And you can try this, you will find 1/2, this 2, 3. This I don't know what we will find, but we will find more greater than this one. Thank you very much. This and this video. See you next.